Hello and welcome in video lecture series Demystifying Blockchain. In today's video, we are going to focus on proof of work consensus algorithm in Bitcoin blockchain. In our previous video, we have seen what is the structure of block, how block looks like, what goes into block header, right? We have seen Merkle root as a representation of all the transactions in the block. In today's video, we are focusing on this nonce part, how this nonce is used to find the proof for a difficult hash-based puzzle. Hash here, I mean cryptographic hash function. In the end, we will also see small demonstration on proof of work, right? We will write a small program in Python and see how all the steps are being carried out. We will also try to vary difficulty depending upon the number of zeros that will be at MSB positions for the hash, and we'll see how we say this is difficult and is beyond the reach of our traditional desktops and laptops. Okay, so let us see. First, we will go through the whole process of mining, what miners do in order to mine the block and get the mining reward, right? So I hope this video explains, like, so after watching this video you won't be required to go to some other places to look into the information about proof of work. Here I will try to cover all the aspects of mining process, right? Some difficult concepts will be simplified so that you understand each and everything that is related to the mining process, right? The first step what miners do is to get some information in order to mine the block, right? So what information is required? I told you in the previous videos that only the header details are fetched for mining, right? Because the body has the transactions and we know there is a representation for all the transactions, that's Merkle root. So Merkle root will be representation for that. Now we see what goes into block header, right? So we have to take care of that. First we have version, right? If we look at previous slide, we have version, we have previous block hash, Merkle root, timestamp, difficulty target represented in terms of bits. I will show you how it's being done, and there is nonce, right? And this nonce is the only variable part that miners try to change in order to get the solution for that difficult proof of work. So first we have version, so it can just easily be fetched from the client that miner has downloaded, right? Then they try to get information about previous block hash from the blockchain itself. Now in order to mine, what is the first transaction? First transaction I have already explained you, this is called as Coinbase transaction, very special transaction. They build that in order to reward themselves according to the protocol and that much of mining reward, right? Then they choose set of transactions that are pending, that are not in the blockchain, from the transaction pool, and they calculate this Merkle root that we have seen in the previous video, right? So then is the target difficulty, that is the target hash. What is the difficulty to mine this, right? So there is a difficulty, so that is represent in terms of bits. So they fetch that from the blockchain itself and they set the time, current time when they start when they start the mining process, right? That is in Unix epoch time, and I will show you how to convert, right? We have the readable time format that we see, then we convert it into epoch time. This is converted into the hex value and that is used for constructing a message M. Now these values, version, previous block hash, Merkle root, bits and current time, these are concatenated and a message is being crafted here, right? You have seen the message. Now what is there? You see, we have seen how these four fields have been concatenated to craft this message, right? Then the miners choose the initial value of nonce, right? Then they concatenate that nonce with the message, and now is the process of proof of work. What is the proof of work process? Is basically you try to hash twice, that is SHA-256 hash is done twice, On what? On message concatenated with nonce. If that hash results in a value that is less than the target, and that target is calculated from the bits itself, if that is less than, then we have the solution. Then we stop the process. If not, what we do, because there is only one variable part, that's nonce. Nonce is being incremented to some other value, right? And the process is again followed until and unless we reach to this, right? We meet this target, we stop. Otherwise, we continue this process. So this is a bit difficult. That's why we require dedicated hardware machines like ASICs, right? Or we say sometimes GPUs for doing this. This is very highly computational intensive task to mine the blocks, right? Now you have seen what is message here. Message is basically you have version concatenated with previous block hash, right? Then Merkle root, timestamp, bits, right? This is first version of message. Then miners concatenate nonce value to it, right? We have seen that here. M is concatenated to the nonce, and then SHA-256 is applied to the header, right? This is basically the header fields, and to form the hash. If that hash is less than the target hash, we say block has been successfully mined, and this is broadcast to all other nodes, right? So this way blockchain is growing with the time, right? Now we have to dig deep into it and see how actually this applies to the real Bitcoin. So for that, I have taken a simple example, and I have taken a very special block that's called first block for Bitcoin's block number 0. You see these are the details, like we have timestamp here. Actually it should have been on the timestamp, version, Merkle root, bits, right, and nonce. So these fields I have extracted, and I have taken those values, converted them into in hex if they are not in hex, and then there is a very special representation called as little endian representation. In order to completely understand the representations that are being used in mining process, that is in Bitcoin, right? So we have two types of representation. One is little endian, another is big endian. So to explain those, we will take simple example of 2 bytes. 2 is 1 byte, and 3 4 is another byte. What big endian says, MSB goes to lower address, right? Lower address means if address starts from 2000, so MSB will go here, and the next address is 2001, 34 will go here. But if we say little endian says LSB goes to lower address, that is at 12, at 2034 will be there, and 2001 12 will be there. So the little endian representation of 1 2 3 4 will be 3 4 1 2, right? So LSB first, then MSB, that is least significant bits will be at lower address space, then followed by the most significant bits. But that is the case in little endian. But if we take big endian, that says MSB at lower address, that is 12, and first 12 at 2000, then 34 at 2001. So this is about representation. So we are using little endian representation here. Okay, so now after taking those values, and we have to take exactly that much of bytes. If we look at how many bytes are these, version is 4 bytes, block hash, previous block hash is 32, Merkle root 32, timestamp 4, difficulty target 4, bytes 4. So we have to take all those into consideration, and we have to prepare exactly the same size of those fields, right? Since the version for block number 0 is 1, we have to take it in 4 bytes, and when we represent this into 4 bytes, this is, you can take it as big endian, but we have to convert it into little endian. What little endian says, LSBs have to be at lower address space. So we have to represent 01 first, then 000000 like this. So previous hash for block number 0 is 0, because there is no block that is, that has been mined before this, because this is very first block for the blockchain, right? In case of Merkle root, if we have this kind of a Merkle root hash here, So if we convert that into Little Indian, what goes there, right? So you have to see that this is in big Indian representation, that is, MSB is at lower address space if 4A is at 2000, but and 3B is at maybe 4000, just for the example, or we can say 3032, right? Then this, in case of Little Indian, the least significant least significant bytes, or you can say bits, that will be taken and they will be represented first. That is, they will go to address 2000 for the sake of understanding. So we will have 3B first, then A3, then ED, just like here. The same goes with all the values that are represented here. In case of timestamp, this is the readable time format. It's converted into Unix epoch, then converted into hex, and that is again converted into Little Indian representation. The same goes with bits, nuns, right? After doing this, we crafted a message like this. We have just to concatenate these values here, right, with the nuns value as well. This nuns has been already decided, because this block is mined way earlier in early 2009, right? If we look at here, it's 2009. So after doing this, we have to go through the proof of work process. So what we are doing here, we are first taking this message, concatenated with the nuns. We do the SHA-256 hash and we get this result. Then again we have to do SHA-256 and we are getting this result. This is again in Little Indian. Now if you want to do it in Big Indian, what you will say? This is in Little Indian representation, and the Big Indian will be the reverse of that, right? Its least significant bytes will be represented in the most significant bytes, right? So we know that this in terms of least significant bits, LS least significant bytes are represented at lower address spaces. That is, 6F will be represented at 2000, but this should have been at the last in terms of Big Indian. That's why it's at last. So we get this hash, and that is the hash that was there, right? You see this 00019D6689 and the 6F at last. So that is it. So 1D6 D6 E2 6F is at last. E2 6F is at last. So this is how you reach to your target hash. But the question is how you decided that this hash that we have resulted here, this hash is less than the target hash, right? We only have the bits. If you have seen, we have bits in terms of hex. We have this number of bits. So we have bits like 0x1d, right? 0x1d, 00FFFF, 00FFFF. How this is the representation of target hash. Since target hash is again 32 bytes, it would have taken a lot of space in the block header. So what they have done, they have optimized it and represented that in very short and concise way, just like you can say fixed point numbers, like floating point numbers representation. I will tell you how to calculate that. First, you have to separate first byte that tells you how many number of bytes are represented for the target hash. If we convert 1D into decimal, that comes out to be like, what is D? It's like 16 plus D is like 10 is A, B 11, C 12 and 13, right? So this comes out to be 16 plus 13, 29. That means your target hash occupies 29 bytes. You can represent these as 1 byte, 29, and these bytes, like these 3 bytes, are the MSBs, that is most significant bytes for that 29. So these are like 00, FF, FF. These are MSBs. Rest are filled with zeros. And how many bytes are still left? These are 29, but the hashes are always, in terms of, if we see SHA-256, they are 32 bytes, right? So 29 are there and 3 are at the top. So 3 bytes here. So how many zeros? 1, 2, 3, 4, 5, 6, 7, 8. Our hash should have at least 8 zeros first, right? At least 8. If it has more number of zeros, that's fine, because we have target hash should be our hash, that is that results from the proof of work should be less than this target hash. That is, if it has more than that number of zeros, that's fine. So at least 8 zeros, right? If we see here, 1 2 3 4 5 6 7 8 9 10, this has more number of zeros, so that is less than that, right? Less than this 0 0 0 0 followed by all other zeros. That's why this is valid. So this bits is the compact representation of target hash, and this can be converted into difficulty, and this is very straightforward process, right? So you know how these bits are, you know, being converted into target hash. So you have to first separate the first byte that gives you the length of your you know, target hash, and before that every byte has to be set 0. Suppose 1D is 29 and we have 29, they are, and the most significant bytes for that 29 are these 3 bytes. Then all 26 bytes are filled with zeros, and before that, because these are only 29, we have 3 bytes, they are all also filled with the zeros. So we have 1 2 3 4 5 6 7 8 zeros must be at least in the hash that is being, you know, that is being that at least these number of zeros, that is 8 number of zeros should be in our hash that results from proof of work, right? So we have seen this, they have more than that, so we are good to go. We say this is the correct solution for proof of work challenge. All right, so for demonstrating proof of work process, I have designed a very simple program for doing all the steps that we have seen in our theoretical explanation. What I am doing here, I am using a Python program, and there is some libraries that I'm using here, like hash libraries for, you know, doing cryptographic hash SHA-256, and there are other things that I'm importing. But very important fields are version, previous block hash, Merkle root, all those fields that are required, and they are part of block header in Bitcoin. What I am doing is that I am generating randomly a nonce, and I am concatenating that nonce with the block header fields, right? Then I am just printing what is their concatenation, but real program goes when I check that they start with certain number of zeros. Let us suppose we will set this difficulty as our hash should start with single zero, then we will consider this as valid hash, and if this is true, then we print what was our first hash value, then second, but our solution is basically the second SHA-256 hash. Okay, so this is like every time I am doing this, if the hash starts with this, then that is the solution. If not, it goes back again and generates the same thing that I have shown here, generates different nonce, concatenates, and again checks does the SHA-256 double hash, right? One first here, then here, right? So if it starts with the single zero, then we say we have found the solution, and we print the nonce value as well as the hash. Okay, all right, so we will try to run this program and see what it displays as the output. We are also printing the time it takes, right? So that's very important in order to evaluate how much difficult or how much time it takes, and how difficulty increases with increasing the number of zeros that we set. For running this program, you have to simply type Python and the name of the file. Here we go. It's very quick. It has taken only like 0.01 second. That's very fast, and that's our second SHA-256, our solution. If you look at that, there is a single zero that is present there, right? So it is very fast, and this was the nonce value in terms of, you know, that we randomly discovered. When we concatenate this value with the header fields, if you look at this, you will find this 199 here. This is our nonce value that is present here as well. So at this nonce value we found the solution, but that was very super quick. That's not the real difficulty. Now if we look at, try to find with 2 zeros, and we'll try to run it again and again, but this time it has taken more time, 0.39 seconds. And see, we set the difficulty to fine, there are 3 zeros, it's still okay, because at least it should be with 2 zeros, and that is, it should be less than the target hash, right? And so this was our nonce value for that. Now increasing the number of zeros here will increase the difficulty, and it will take more time to mine and find the solution for our challenge, right? That's why, the real difficulty for Bitcoin is way beyond the reach of our normal laptops, desktops, right? See, it has taken 7.1 seconds now, and this is the hash with 3 zeros. If we try to find one more time with 4 zeros, now it will start taking more time. Okay, so like more than 4, it will be very hard for us to wait here and see when it finds that solution. See how much time it's taken for 4 zeros now. All right, we have seen how much time. It's like 258 seconds it has taken to mine a block with the difficulty set as 4 zeros. So you can imagine how hard it is to find, right, if you have 20 zeros and more than that. So I hope you have understood the process of mining completely now. If you like the content, do subscribe to the channel, learn to apply, and hit the like button of the YouTube video. See you in the next video. Bye bye.